So, gas laws quiz. On the first one, you're told that a flask contains 1.55 cubic centimeters of hydrogen collected under a pressure of 22.5 kilopascals. What pressure would have been required for the volume of the gas to have been 90 cubic centimeters, assuming that we have not changed the temperature? So we're solving for P2. Many of you got written on your paper, rearrange first. Don't just plug in numbers. Don't not write an equation. It's sloppy form. It's just bad on all grounds if you're going on in science at all. You have to be accustomed to writing that equation. The other thing, and a few people made mistakes this way, list your variables. Especially if you're taking physics next year, I will beat you with the stick of listing your variables. List your variables. So I do that, and then I do P1, V1, P2, V2. This is what I'm looking for. Or, yeah, that's what I'm looking for. 22.5 kilopascals, 155 cubic centimeters, 90.0 cubic centimeters. Does that take me a second? It does. It's not like you have any place else to be. And on top of that, when we do larger equations, and especially, again, if you're taking physics, we do much larger equations. We mesh equations. We do all kinds of craziness. So you have to get used to listing those equations, or listing those variables. So once you have the variables listed and you have your equation rearranged, now it's down to plug and play. So we're just going to plug these in. Okay, so we get it plugged in. 38.75 kilopascals is our other pressure, and we only have 3 sig figs to work with, so this becomes 38.8 kilopascals for our second pressure. Okay, most people did okay on that. Some sig fig errors, but for the most part, you got this unless you made an algebra error. All right, so number 2 is volume and temperature. You're solving for T2. These are the ones where you're most likely to make an algebraic error. So I seriously actually recommend do all the long steps. I've been doing algebra longer than you've been alive, all of you, and I still do this sometimes. And, you know, at this point I can skip steps, but I find that if I get in a hurry and I skip steps, I screw up. So sometimes I don't skip steps. The common thing with this kind of problem is that you end up solving for the inverse. Okay. So we'll actually just get rid of that. Oops. And move this up. Okay, so we list our variables. T1 is 67 degrees Celsius. Which is 340 Kelvin, and V1 is 150 milliliters, V2 is 50.0 milliliters, and we're interested in T2. So we have an equation we're ready to plug in, so T2 is equal to 50.0 milliliters times 340 Kelvin over 150 milliliters. And what we get for T2 is 113.33, etc., repeating. Kelvin, we only have 2 sig figs to work with. So T2 can either be expressed as 110 Kelvin, or you can convert it back to Celsius, and it's negative 160 degrees Celsius. Either of those is an acceptable answer. Okay. Number 3, this is where the steps that I mentioned, things like rearranging your problem and listing your variables, are extra helpful. So we know this is pressure temperature. P1 over T1 equals P2 over T2. And once again, because I'm mean, we're solving for T2. So this time I'm not going to do each of the steps. We'll just go ahead and write that. So I've got my equation rearranged. Now, variables seem to be rather thin on the ground, as it were. I don't have a whole lot to go with, do I? So P1 is unknown. All we know about P2 is that it's 2 times P1. It's been doubled. And what we're interested in is T2. How can I possibly solve this? Algebra! It's magic. Here comes the magic part. So P2 is equal to 2 times P1 times T1 all over P1. Does everybody see how I substituted that in for P2? Because that's what it's equal to. Well, then your P1s cancel out. And what are you left with? T2 equals 2 times T1. It's cool. I do toss a couple problems like this in here and there, you know. The volume is tripled, the temperature is cut in half. What's the new pressure? Because you should be able to do these sorts of algebraic relationships. So T2 equals 2 times 200 Kelvin. T2 is 400 Kelvin, or 127 degrees Celsius. Now we only have 2 sig figs, so the only way to express that Kelvin temp with 2 sig figs is in scientific notation. The Celsius temperature is pretty easy to express in scientific, or with 2 sig figs. 127 rounds to 130, and you've got 2 sig figs. Questions on that one? So these are problems where we're changing more than one thing. So we have P1 V1 over T1 equals P2 V2 over T2, and we're solving for V2. So what we end up with is P1 V1 T2 over T1 P2 equals V2. And I get tired of saying PVT because they all rhyme and it drives me crazy. So again, I strongly recommend, actually I demand, that you list your variables. Let's cut to the chase. I don't recommend, I demand. P1 is 772 torr. That's pretty much normal atmospheric. The volume of this balloon initially is 4,400.0 liters, and the temperature of the gas at ground level, this must be someplace warm, is 30 Celsius. A few of you caught that 30 didn't have a decimal behind it, so you really only had 1 sig fig, which is terrible. I solved it with 2 and with 1, and I didn't take off imaginary points. I didn't take off imaginary points if you used 2 sig figs, but I did if you didn't use any notion of sig figs. So it's going to travel way up to the top of the atmosphere in the stratosphere, and the pressure there is very, very low. It's less than 1 torr. And the temperature there is very, very low. It is negative 82.5 Celsius. So let's get these converted. This one's 303 Kelvin. This one is 190.5 Kelvin. And so now we have everything we need. We're looking for V2. And so V2 is equal to, we have 772 torr times our initial volume times our final temp over our initial temp, our 303 Kelvin, times our final pressure. Okay, so what we get is a V2 of 2,703,306.17 blah 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 liters. Expressed with 2 sig figs, this would be 2.7 times 10 to the 6th liters. With 1 sig fig, 3 times 10 to the 6th liters. Either way, it doesn't matter. We're told that this thing's going to pop if it exceeds 1.15 times 10 to the 4th liters. So this baby is gone. This is exploding in the upper atmosphere. And somewhere a National Oceanic and Atmospheric Institution scientists just lost their job because they didn't do the engineering calculations on this right, and they lost a weather balloon. They actually do, if you've ever seen footage of weather balloons launching, when they launch, they look like they're totally underinflated. They look very sort of spongy and like they can barely lift off because there's so little. You look at it and you think there's so little gas in there. How can that thing even lift? Well, they're traveling up in the atmosphere where the pressure is significantly reduced. So somebody somewhere is doing these kind of calculations to look for on the engineering end to say, well, what volume needs to be allowable as a maximum volume for this balloon? Because these are not like little latex balloons. These are a heavy-duty mylar, and they don't have the kind of give that we think of in a latex balloon. So they have to be capable of accommodating the volume of the gas at upper atmospheric pressures and temperatures. So somebody's doing these calculations. Okay, last one. So again, we've got 3 factors, and now we are looking for V2. So we have P1 V1 T2 over T1 P2 equals V2. We list our variables. P1 is just 1 atmosphere. V1, 750 milliliters of gas. T1, 20 Celsius, a reasonable day at sea level. Okay, so here we have sort of the other extreme. We're putting something into the ocean, and of course the pressure on gases underwater is tremendously higher than in the atmosphere. So we want to know what the final volume of the gas is. It's also cold down there. So we've got our equation rearranged to solve for V2. We have our variables listed. And so we just plug in. We get a raw answer of 414.520633, on and on. Milliliters is our final volume. If you allow for 2 sig figs, this is 410 milliliters. If you go with my goof and realize that that really only had 1 sig fig, then you get 400 milliliters. Okay? Questions, comments, or concerns? The biggest thing I can tell you, rearrange your, I expect this of you. Write your equation, rearrange your equation, list your variables. On the small test, large quiz, the quest that will end this chapter probably on Friday, if you don't do those things, I don't give you credit. Period. So write your equation, rearrange your equation, list your variables, and then you get your credit. Okay, so let's move it along, shall we?